Hello. Today we will be talking about horizontal control and in particular how to do the calculations of the positions of points easting and northing using different methods. And today specifically we will be talking about two special formats of triangulation, which are the resection and the intersection. So in particular in this presentation we'll be talking about resection. So what is resection? What is intersection? They are two specialized forms of triangulations with limited number of control points, and usually there are three control points. So in the resection we will occupy the unknown station, and then we'll do the measurements to the other control points, which are at least three control points. As you can see here, we will take the instrument and set it up on the unknown point, which is usually we call it control P, and then we will be measuring the angles between point A and point B, and then point B and C, which is this angle. So this is between A and B, this one is between B and C, and for the beta angle, which is between A and C. While for the intersection, we will be doing the measurements from the known points. So we will put the instrument on the control points, not on the unknown points, and we will do the measurements from all these unknown control points to the unknown point, and here we will be measuring 6 angles if we have only 3 control points. If we have more control points, either in the resection or in the intersection, we can add more control points. This will strengthen the solution, but usually these two particular problems, they are done using 3 control points. So let's start with the resection. And the resection, we have, as we said, unknown station that we will set up the instrument on it and do the measurements to the other 3 control points. In this kind of a problem, with the unknown point can be inside the triangle from the control points, the 3 control points, and here are the point is inside the triangle ABC, and the other case is that the point, the unknown point, is outside. So this is the triangle of the ABC, the control points, while our unknown point is outside. So the measurements from this point, the angle, of course this is a kind of triangulation, so all what we need is to measure distances, measure angles. We do not have any measurement of the distances, and because of the control points here, so we already have a control point, because in the triangulation we have to have at least 1 control point. So we have 3 here, 3 control points. Now, do we need a measurement of the azimuth? We can do that, but since we have the coordinates of the 3 control points, we can calculate the azimuth of the azimuth of line AB. We can calculate the azimuth of line AC, because these are lines with their ends on control points. The same thing here, it is AB and AC, and we can also calculate the azimuth of line BC or CB. So what about the distances? The distances also is not needed. They are not needed because already we have the control points. We can calculate the distances between them. So either in the solution, either you will put the distances or you do not put the distances, because 3 control points are enough for determining the azimuth, the direction of the orientation of the network, and the location of the network. So in its simplest configurations, we will have an unknown easting of point B, northing of point P, and we have, of course, known easting and northing of B, known easting and northing of A, known easting and northing of C. So we have total of 4 stations. 3 are control stations. For the distances, we need not measure any distance. So we will have in the minimum, we will have EP and NP. We have the coordinates of these 3 control points, and the measurements will be angle beta and angle alpha. These are all what we need. When the point is inside, we will measure 3 angles, alpha, beta, and gamma, and we have the coordinates of the 3 points. Here, as we said, we can have the azimuth calculated from A to C. We do not need any azimuth, we do not need any distance measurements in this case. We just measure these angles and we'll be able to calculate the coordinates E of point B and northing of point B just from measuring the 3 angles. We will see actually in the examples that we will use only the minimum, which is the coordinates of the control stations, and we will do another examples where we measure more. We will measure distances, we will measure also azimuths, and we will see that the azimuth is the solution is still the same. The resection is a famous problem in triangulation. It is also called single point resection because we are calculating one unknown point, or we call it 3-point resection because we have 3 control stations. So whatever you want to call it, it is okay. Now, of course, the 3-point resection is a form of a triangulation. We mentioned that, and this is a favorable method when we cannot occupy the control station. We cannot reach the control station, so we can reach the unknown station, and that's why we take measurements from that unknown station. Since we cannot occupy, we cannot access the other points. Also, since we are occupying just the unknown station, so the number of setups will be reduced. So this will actually save time and save the cost because we are not going through all these points, setting up and doing the measurements. Due to the number of measurements, due to the limited number of measurements, so the accuracy level of this triangulation will be kept into the 4th order. But if we add one more point or we measure more angles, then this will be considered or can be considered a 3rd order, and this is the maximum. If we have just a strong triangular figure, and the measurement of the angles, it was very, very accurately done. So to ensure the strength of the triangles that we are doing the resection with is that first the location of the point should be distributed in a way that the interior angles, they will be around, like these are the interior angles here, the interior angles here be between 60 and 120, and this will add to the strength of the figure itself. Redundancy, usually we do it with the 3 control stations, but if we add one more control station, that will be better for the redundancy of the solution. We will have more measurements, and this will strengthen the solution. Also, the measurements themselves, first we measure these angles, alpha, beta, and gamma, or alpha and beta if we have only 3 points, but also we can measure the exterior points, the exterior angles. So not only the interior, also on the other side, or we can measure, for example, this angle, or we can measure this angle. So we can do the different combinations of the measurements from the interior and the exterior. Also, we have to make sure that the sum of these angles should not vary more than, like the angular disclosure, should not be more than 3 seconds, and this will add to the level of accuracy of the solution. And also that when we do the measurements, we do not do the measurements just one time. We can measure 2 to 4 times. In triangulations, in some situation, surveyors used to measure an angle 35 times to ensure the accuracy. So here is the unknown station. We have the control station on other locations. We will occupy the unknown station and do the measurements. Actually, if we take a horizontal projection, we will be measuring alpha and beta as a minimum. If we want to measure exterior angles, we can do that. But for now, this is what we measure. And also, I did not mention in the previous slide that we will do the measurements 2 to 4 times in facelift and face right, just to ensure the redundancy of the measurement. So in addition to the measurements, we need the coordinates of 3 control stations. These control stations will be used in the solution. We do not need to measure any azimuths. We do not need to measure any distances because we can get the azimuths and distances from the control points. So how can we solve? As with other systems of triangulation of horizontal control solutions or networks or layouts or systems, we want to do it using a triangle solution and this square adjustment. Triangle solution, we said we can do the measurements from different routes, and this will give me different answers every time. Of course, do not think of the different answers as a completely far away, very different solution. No, it will be there will be some differences. But when you are doing the least square, as we said, the least square is the best method, the best results from the available measurements. But the disadvantage is that we have to come up with the initial values of the unknown point P, easting and northing. Of course, through the years, we have different theories, we have different practical methods on measuring, on calculating the estimated or initial coordinates of E and P, which is actually the triangular solution. So we'll use a triangle solution method to calculate a solution from any route. Doesn't matter. We just need initial values, and they will plug these initial values in the least square adjustment solution. The resection does not have any setups on the control station, so there are no measurements from the control stations or the known points to the unknown points, and this is one of the disadvantages of the method. We have to make sure that when the point is inside the triangle, the solution is normally perfect, but should be outside the danger circle. What is the danger circle? Is that all the points will fall on the circumference of a circle and subtended by the same chord. This is a rare position, but it can happen, and this will not be able to find a solution to the problem. So what are the measurements when we are doing the point inside the triangle? In the triangle, which triangle? The triangle made by the control points. So these are the three control points, and then we will have the point is inside, and this is the most ideal situation. What do we have to measure? We measure alpha, beta, and gamma, three angles that are measured, and that's all. These are the measurements, alpha, beta, and gamma. The angles unknowns, they are the P. So always we have to think of the given quantities, measurements, and what are the unknowns. One method of doing the solution, not only the initial estimates for the least square, but also the solution, the triangular solution, it is called the Enstra formula. It is the proof of this formula is a little bit lengthy and complicated. Not that complicated, but it needs light. We are not here for the proof of the method, but the method works, and all what we have to do is calculate three quantities, K1, K2, and K3 from cotangent of angle A, and this is angle A, and this is angle B, the whole angle of the triangle, and this is angle C, and C opposite to it there is the gamma. A is alpha and B is beta. So we will be doing K1, 1 over cotangent A minus cotangent alpha, the opposite angles. And for K2 it is cotangent B and cotangent beta. For the third one, this is K3, it's cotangent C minus cotangent delta. Here it should be gamma again. This is gamma. So these are the three quantities that we want to calculate, and these are only dependent on the angles, A, B, C, interior angles of the triangle, and the central angles, alpha, beta, and gamma. So what is EA? It is the first control point, and EB is the easting of the first control point, the second control point, and the third control point. And for the N, which is the northing of point B, we use the northing of point A, the northing of point B, and the northing of point C, always divided by K1 plus K2 plus K3. 3. So this is a straightforward solution. You can put this thing in these formulas in Excel and just plug in the EA and A, EB and MB, and EC and NC, and you will get the solution right away. You do not go into, unless it is the exam, of course, you have to do the calculations. Now, when the point is outside, so what do we have? We have coordinates of control points A, B, and C, and the measurements from the unknown points to the other points. The angles, they are alpha and beta. No angles other than these from the control points to the point are measured. No distances are measured. No azimuths are measured, because all of that can be done from these two known the three control points. So let's take an example where we have the point is inside. We have three control points in the blue circles, and we have three central angles in the red. And now, what do we have? We have the coordinates of the three control stations, A, B, and C. We have the measurements, which are the angles from always the central point, or the vertex is P, and 1, 2, 3. These are three angles, and they are entered as degrees, minutes, seconds. What is the approximate coordinates? Triangulation method, we can get the coordinates of, but actually when we are doing the Triangulation method, this is one solution method, it will be the solution using the triangle. So this is the formal solution for that, but you can do the solution and you take the values and you treat them as if they are initial values for the least squares. What are we going to do here? We have the stations, we have the side links. These are from the control points. We can find these if we want. And then we have the interior angles. The interior angles, how can we calculate the angle A, angle B, angle C? These are calculated using the cosine law, or law of cosines, where, because this is a triangle with all sides they are equal, so the relationship for the starting point of solving for the angles here is the law of cosines, which says, for example, AB square equals, this is the opposite to this angle. We are calculating for angle C. So the opposite is AB. So AB square equals the other two sides, which are AC square plus BC square minus 2AC BC cosine the angle C. So the only unknown, we know all these sides, the only unknown is the cosine. So rearrange the equation, calculate cosine C, and then calculate the point C. And this is what we are doing. So we did this for the three angles. And then what do we have? We need to have the k's, which are 1 over cotangent A minus cotangent alpha. So these are the where is that? Central angles, alpha, beta, and gamma. Actually, these are in should be in Greek letters, but it's okay. Alpha, beta, and gamma. This is the amount of the angle in degrees, minutes, seconds, and in radians. And then we calculate K1, K2, K3, and then we will substitute in the formulas for the easting and northing of the point P, which is unknown. So this is the solution using the triangle solution method, and the same numbers we can take them and do the initial estimates for the least square method. So now, how can we want to do it using the least square adjustment? Least square adjustment, it is done as usual in the adjust program. We have the number of distances. We don't have any distances. We have 0 distances. Number of angles we measured only 3 central angles. Number of azimuths is 0. We did not measure any azimuths, no distances, and 3 angles. Number of control stations, we have 3, and the total number of station is 4, including the control point. So here, 0 distances, 3 angles measured, 0 azimuths, 3 control stations, and total number of stations of 4. These are the control station coordinates A, B, and C, followed by the unknown station, because we only have one station unknown. And these are, we can take them from the solution of T-Anstra method, the solution of triangles. Now, what do we have here? We have three angles, ABP. So here, A, P, B, and we have BPC. These are the three angles that we have. We enter them, we enter their values, and the standard deviation plus minus 15 seconds. You will see the solution now. The solution here at the end. Of course, we have the full output of the file, but these are the results, which is one line showing the coordinates of point P. See, it's very close to the initial values because we took it from the solution of the triangles. In AutoCAD, this is the solution from AutoCAD. The original problems was first done in AutoCAD. We know these angles, but we put them as different angles. We add some noise. So compare if you want. This is the solution after the least squares, and this is the original solution. Of course, the differences, they are coming from the misclosure, or let's say we add some errors to these central angles plus the geometry of the problem. In example number 2 here, we want to add more observations. So we said in the original problem of the resection, we have only angle measurements, which is angles in red 1, 2, and 3. Now we want to add distance measurements. So we'll go to the field and we'll be measuring two distances, one between A and B and another one between B and C. We can go, actually we measured the third distance, which is so 1, 2, and 3 distances. Now we want to have the measurements as 3 distances and the 3 angles. The control information, it is A and B and C for the 3 control points, and we have the approximate coordinates of the point P. So the data file for the least squares, it is, we have 3 distances, we have 3 angles that we want to measure, 0 azimuths, 3 control points, and 4 total number of stations. So here we have the stations, the control stations. These are the coordinates given, and here is the estimated coordinates of the unknown point. Here are the 3 distances, and we are adding because they are some kind of a control distances. So we measure them very accurately, plus minus 1 centimeter, which is 0.01. And we have the angles here, and these angles, they were having plus minus 15 seconds. Now we want to run the profile, give it to the adjust, see the results, and these are the results. If you compare it, or see the first looks here, it looks like this is the same answer. We will at the end, we have one more example, and then we will do the comparison, and you will see how does it compare to each other. So the first example number 1, it was only the 3 control points. In the second example, we added 3 distance accurately measured distances between A and B and B and C and C and D, and we have the result. And now, so in example number 3, we are adding more observations. So at the beginning, in example number 1, we had only one type of observation, which are the angles. In example number 2, we added distance observations. In example number 3, we added azimuth observations. So we want to see how is the solution after doing these 3. And we said the original problem, we don't have to measure distances, we don't have to measure any azimuth, but we did. So here we have the 3 coordinates of the control points. We have the measurements of 3 distances, which is distance 1, 2, and 3 in purple. And we have 3 angles, which are alpha, beta, and gamma in the red. And we have the azimuths in the green. Yeah, these are the green. Approximate coordinates are for point B are the same. And now let's do the file for the adjust program. So the number of distances that we have already, we measured 3 distances, we have measured 3 angles, we have 2 azimuths, 3 control stations, and 4 total number of stations. These are the 3 coordinates of the 3 control stations. This is the estimate of the unknown point. these are the three distances with plus minus 1 centimeter standard deviation. The angles, they are 3 with plus minus 15 seconds. And for the two azimuths, we have azimuth AB and azimuth BC. Can we add azimuth, one more azimuth, which is the azimuth method, for example, AC or CA or whatever? Of course we can. But here we said we just measure two azimuths. So these are plus minus 1 second, which means they are known very accurately. Let's go to the answers and see what we got. The results from example 1 with only the control points. Example 2, the control points plus, of course, example 1, the control points plus the angle measurements. Example number 2, the control points plus the angle and distance measurements. And example number 3, we have 3 types of observation, which are the distances and the angles and the azimuth. Now here is a comparison between the 3 solutions of the same network, but the first one with angle observations only, and the second one we had angles and distances, and the third one we have angles, distances, and the azimuths. As you can see, it is the same solution. One reason for that is that the network is a strong one. Secondly, the added measurements, they were accurate, plus minus 1 centimeter, and for the azimuths it was plus minus 1 second. These are almost measurements without errors. They are very excellent measurements. This is the fourth example where the point is outside. So this is the triangle from A, B to C. These are the control stations. This is control angle station A, station B, and station C. And we have, this is the triangle if you want to draw it. The triangle is here. So this point P is outside this triangle made by the 3. What are we going to observe? We are observing only these 2 angles, and we want to calculate the coordinates of point P. Of course, if you want to go to the solution using triangles, it is a tedious one, but we will use it to just get the approximate coordinates of these of point B. So this is the only thing, is that we want to find a way to find the approximate coordinates of point B. Other than that, the solution is straightforward. In this example, we are given the 3 coordinates, the coordinates of the 3 control points. We have measured theta and phi, which are 48 and 41, these 2 angles. And then we have the azimuths and we have the 2 distances, and these are the approximate coordinates. So the number of distances that we have, because we assume that we have 2 distances that we made, and it is plus minus 0.001, which means 1 millimeter, which means this is a known distance, very well known distance. When we give it a small standard deviation, that means it's almost known distance without any errors, only 1 millimeter plus minus. So what do we have? We have 2 measurements of the distances, 2 measurements of the angles, which are these angles. And then we have also 2 measurements of the azimuths, which are azimuth B, C, and we have azimuth AB. Here is the azimuth AB, and this is the azimuth AB. This should be a black color. These are the 2 angles, and these are the 2 distances, and this is the approximate coordinates, and these are the known coordinates of the 3 control points, and 4 is the total number of stations. Once you will find this is the solution, and as simple as that. One more example, which is example 5. We have the same thing. The point is outside the triangle. The same thing, using the only thing that we have to take care about in calculation wise is to calculate the approximate coordinates of point P. As we said, we have to find a way, like the Henstra in the previous one, but here when it is outside, we have different also methods to approximate the solution. Now, for the point outside, we have the coordinates of the 3 points. We have the measurements of 2 angles, which is angle 1, call it theta, and this one is the phi angle. We measured them, theta and phi. Azimuth of AB and BC, AB and BC. These are 2 azimuths, and the distances AB and BC, AB and also BC. The distance and the azimuths we will measure. And this is the approximate coordinates of point B. So we will prepare the final number of distances. As we said, we have 2 distances and 2 angles and 2 azimuths, 3 control stations, and 4 total number of stations. These are here. Then we will give the file to the adjust program, and these are the results. Always we compare the AutoCAD actual coordinates with the coordinates that we got from the least square adjustment. This is the end of the presentation about the resection method.